Okay, guys, in this video lesson, we're going to go on to our next major term inside this unit, which is power. Okay, so when you think of power and what power is, or things that are powerful, okay, a lot of people associate the word power with force or strength or big kind of things like that. So, like a big semi truck is very powerful, or that offensive lineman is very powerful. Okay, and there's nothing wrong with that because that idea might be correct, but it has another part to it that we need to be aware of. Okay, so when we look at this idea of power and what power is in the world of physics, okay, it's very specific, very much how work was very specific and energy is very specific. So we use the word in a way that also deals with that idea of strength and providing a lot of force, but it's not just strength or force. It also has a time component to it. Okay, so power is actually a rate. All right. That's something that might be a little bit new or something like, oh, wait a minute, power is a rate. Like, yeah, power is a rate. Very similar to like how velocity is a rate, right? Velocity was meters per second, or it was a distance per time, okay? Power is the same idea, but it's how much work can be done per time or energy converted per time, okay? So if we take a look at our formula for that, we say that power is our work that we can output divided by the time it takes us, okay? So you could put in a lot of work. Like you could put in like 10,000 joules of work, and if it takes you hours to do it, you're not very powerful. Okay. However, if you put in 10,000 joules of work and it takes you 2 seconds to do it, well, that's 5,000 watts of power. So that's, it's a lot of power there. Okay, so that's what we're kind of looking at. It's about the work you put in and how fast you can get it done. So power really has two components. It's the work and the time. So things that are powerful can do things quickly also. All right. Now, this idea of power in this formula, it's good in its form, but because work can be broken down further, we might want to take a look at that in different forms. Okay, so if we go to the iPad here, we know that power is work divided by time, but we also know that work is our force times our displacement. Okay, so now we have force times displacement divided by time, but displacement over time, if you remember, that's velocity. Right? So another way that we can look at power, you can say power is also equal to the force times the velocity at which something is moving. Okay, so that's kind of another one we can look at. Now, on the same token, power, of course, is work over change in time. But we also know that work results in a change in energy. So what we can say is that power is also the change in energy over a change in time also. Now, keep in mind that changes in energy can be broken down even further also in this, all right? So we end up with two additional equations that we can use for power that become useful for us, all right? So power is change in energy over time, and power is our force times our velocity, okay? Not as often as used as this, but they are still very important. This is a very different look at this in terms of what we have for this one. So this one's kind of unique to have a look at that one, okay? So those are our equations. So next thing we want to do is take a look at what are the units for power, okay? So we know we have, work divided by time, okay, and work is in joules or the Newton meter. So we have joules divided by seconds, okay? So it's joules over seconds. So do we just say it's joules per second? Okay, that would work, that's actually fine. But because we like to bring together our units into like one word for us, we now use the term watts here. So you may have heard of the idea of power being power in watts, like a light bulb kind of stuff. That's kind of the same idea here. So how many watts we have this? All right. So basically 1 watt is when 1 joule of work is done each second. Okay, so a joule per second is a watt. All right, so that's what the watts are. They're joules per second. So our label in power is joules divided by seconds, but we just rebadge that as to being 1 watt. Okay, so now if you did it joules per second, that's fine. Okay, there's nothing wrong with labeling it joules per second, but it's the same thing as being a watt. Okay, so be ready for that because we'll probably tag power in watts all the time. So let's take a look at this idea of power and what it kind of means to us. So we're going to use electricity and lights to kind of be our example here. So a 100-watt light bulb, okay? Now, wattage in light bulbs has changed drastically over the past 10 years, okay? So when you guys were little kids, like little babies and stuff, the light bulbs that we used in houses were incandescent light bulbs. So they drew most of their energy to heat up the light bulb and to make a filament glow a white hot kind of kind of color, and that lit up our rooms. Okay, so those are very much power consuming light bulbs. They consumed a lot of energy in a short amount of time, and most of it was lost to heat energy. So it's a very inefficient way to light our houses. Now, with increasing technology, we went to something called CFLs, or compact fluorescent lighting. Okay, they're basically the same as the fluorescent lightings in our room, just spun into a spiral. Those little spiral light bulbs. They were much better. So you could take, let's say, a normal 60-watt light bulb, and it would bring it down to like 13 watts instead. So it's a huge improvement of energy savings. And then LED technology got even better, and so now that same light bulb is about 9 watts of power. So it's interesting when you buy light bulbs, because when you buy a light bulb now, because a lot of the adults grew up with an old system, they always on the packaging say, hey, this is a 9-watt light bulb equivalent to 60 watts of power. So they're saying the brightness it provides is equivalent to the old style light bulbs. I assume as time goes on, that will disappear off the packaging when the consumers don't need that extra information anymore. Kind of cool. Anyway, if we are using an old 100-watt light bulb, okay, you may have some of these things like in a spotlight or in your garage, something like that. These are really bright. So 100-watt light bulb were not like a normal household light. They were like a garage light or a floodlight or something like that that we used to use. That would consume 100 joules of energy for every second you had it on. Okay, so if you think about that, you had this thing on for a minute, that'd be 600 joules of energy. Okay, so they consumed a lot of energy very quickly, these type of light bulbs. All right. So that's kind of an idea of what we're going to use for our units, or watts of power. Now, let's do some practice, okay? So here's our scenario. What we have is a mountain road, okay? So if you think about a mountain road and how mountain roads are designed, okay, it's pretty rare that you have a road that goes just straight up a mountain, okay? Instead, they tend to zigzag back and forth, or they switch back and forth, all right? So if you think about it, if we had this gigantic mountain, okay, and you have this little car, it's not like we take a car and go straight up the mountain. We don't really do that. We tend to, make it do this, back and forth, back and forth, back and forth, to get to the top of a hill or a mountain, that kind of stuff. We do it for a couple reasons. One, it's conservation, because a road that goes straight up and down creates kind of vertical lines on a mountain, which then causes a lot of erosion in the ditches, that kind of stuff. So one thing is, by having the roads zigzag back and forth, you're actually creating a way to conserve the soil and that kind of stuff. So that's good in terms of the environment. But in terms of the physics behind it, why do we do it in terms of our cars? Let's talk about that. All right. So here's what we're wanting to think about. Why is this an advantage for us in terms of power required, work done, and energy converting? Okay. So by doing this, does it require more power, same amount of work, less work, more energy converted, less energy converted? What's that kind of difference? So for each one of these three things, give yourself either a more, a less, or the same in terms of what goes on here by having a road switchback versus go straight up a mountain. Okay, so pause it, think about it, maybe even write it down, and then come back to the video and we'll give you an answer. All right, so let's take a look and see what's kind of going on here. All right. Now, if we have a starting point at the bottom and an ending point at the top, the overall vertical distance, so the height that we reach in our mountain, is the same no matter how we get there, okay? So if we have the same height, the amount of work is the same, okay? Which means if our work input's the same, our energy is the same. So it is no less work to get to the top of the mountain, and it's no less energy to get to the top of the mountain. That's exactly the same, all right? So that's one thing. So if they're not different, why do we do it, okay? Well, let's go back to the idea of ramp, okay? Before we said we use ramps to reduce force, even though the work was not the same. Well, kind of the same idea here. By using a switchbacking road that takes that path, it makes it longer, okay? So you can provide the same amount of work, but because you're moving over a longer time period, switchbacking back and forth, a lot more distance there, okay? Because our distance goes up, that means our force goes down, right? So it's less force, and we have more time. So the overall power, or horsepower in a car, we'll call it, needed is much less, okay? So the idea of behind these roads is that we get a larger amount of time in here primarily, okay, which means more time, you have less power needed for that, okay? So a less powerful car can accomplish the same thing that a more powerful vehicle would be able to do on these kind of roads. All right. Plus, with the angles and that kind of stuff, there's friction there for icy roads, that kind of stuff too. But we won't even get into that kind of stuff too. So, all right, guys. So that's our first one. Let's take a look at this idea of a numerical practice now. All right. An electric motor lifts an elevator 9 meters in 15 seconds by exerting an upward force of 12,000 newtons. What power does the motor produce in watts and kilowatts? Okay. So now we have some information here. We have a distance that's been pushed. We have the time. And we have a force. So we have height, force, and time. So from that, let's find the power produced in watts, and then let's convert it to kilowatts. Okay? Go ahead and pause the video, and we'll give you the solution here in a second. All right, so here we go. First thing we want to make sure we realize that power here is going to be our force divided by time. So you notice that instead of writing this as work, we just wrote the equation of force divided by time in here instead. Because we were given a force, and we were given our distance here. So we have our time. So these are the three things we were given. So I just jumped right to making this force times distance here. Again, plugging that in, we have our 12,000 newtons times our 9 meters divided by 15 seconds, and we end up getting 7,200 watts. Okay. A lot of times, because a watt is not a lot of energy, if you think about that, 1 watt is 1 joule per second, and joules are kind of small. So a lot of times you'll see that wattage is reported in kilowatts or thousands of watts packages. So we end up with 7.2 kilowatts of power needed to lift that. Okay. So if you're actually going out to buy an electric motor, okay, and electric motors come different ratings in them. So one thing you would look for is how much power do I need that motor to have. So you want to have a motor that's capable of producing 7.2 kilowatts of power per second at all times. Okay, so that's one thing. So if you had a 5 kilowatt motor, it couldn't do this that fast. If you had a 10 kilowatt motor, it would be more than powerful enough to make this happen. Okay, you wouldn't have to use all of its power, but it'd have enough. All right. Okay, guys, that's where we're going to finish up this video lesson here. In the next lesson, we'll move on to something called torque. Thank you.